Area and estimating with finite sums. In this video, we'll use finite sums to calculate distance traveled and displacement. To begin with, let's assume that we have an object moving in one direction along a straight line and let v of t be the velocity of that object at time t. Let's also represent the position of that object on the line by s of t. Now we know from calculus 1 that velocity is equal to the derivative of position with respect to time, or that position is the antiderivative of velocity. Now remember, there's many antiderivatives for velocity, so if we let f of t be any of those antiderivatives, then we know that the position function is equal to the antiderivative of v, f of t, plus some constant c. Now, if we want to talk about distance traveled, the distance traveled by an object is its position at the end time minus its position at the beginning of time. So that would be s of b minus s of a. Now we can write that function s in terms of an antiderivative f. So s of b here we could write as f of b plus f of c. And then we subtract off s of a, which is f of a plus c. When we do this, the two c's cancel each other out, and we're left with that our total distance traveled is equal to the antiderivative of v at the end point minus the antiderivative of v at the beginning point. So looking at this, we can see that it doesn't matter which antiderivative of velocity we use to calculate the total distance traveled. We can use the actual position function, or we can use any antiderivative. All right, so often when we're talking about velocity, we don't know what the formula for it is. We might be able to calculate the velocity at certain time points, but we don't know an exact formula. When this is the case, we still want to be able to approximate the total distance traveled. So here's how we're going to do it. First thing we're going to do is take the time interval a to b and subdivide it into n subintervals of equal width delta t. So we're using delta t because it's change in time, right? So each time interval is the same width. Then in each subinterval, I'm going to choose some time point, and we'll call it t sub k. Once we've done that, if our delta t, if the width of each time interval is small enough, then we can guess that the velocity or say that the velocity on that time interval is nearly constant. So what we could do is we could say, okay, the velocity on that time interval is the velocity at time t sub k, and I know the total distance traveled on that time interval is approximately going to be equal to the velocity there, the vt sub k, times how wide my interval is, which is delta t. Now, if I want to figure out my total distance traveled on that time interval, I just add up the approximation of the total distance traveled on each subinterval. Now let's look at that formula again. We said total distance traveled is equal to this formula right here. But that formula should look awfully familiar. In our previous video, we saw that that equation there is the approximation for the area under the curve y equals v of t, see our function evaluated at some point in the interval, times the width of our interval. So we have just tied our total distance traveled to the area under our velocity curve, and that's pretty cool. So let's do an example. You're sitting on a bank of a tidal river watching the incoming tide carry a bottle upstream. You record the velocity of the flow every 5 minutes for an hour with the results in the accompanying table. About how far upstream did the bottle travel during that hour? Find an estimate using 12 subintervals of length 5 with first using the left endpoint values, and second, using our right endpoint values. All right, so the first thing to notice is look at our time. Our time is measured in minutes. Our velocity is measured in meters per second. When you're working on word problems, you want to make sure you're consistent with your units of measurement. And we're inconsistent here in that here time is measured in minutes and here time is measured in seconds. So we're going to need to choose one of those units to do everything with respect to as we go along. All right, so let's start with our endpoint values. The time interval we're looking at, AB, is 0 to 60 minutes, and we're going to divide it into 12 subintervals. That means our delta t is going to be equal to the width of our time interval divided by our number of subintervals. So that's going to be 60 divided by 12, which is 5 minutes. So now since the speed and the time were measured in different units, we want to make sure they're the same units of time. So we're going to convert everything into seconds. So 5 minutes is equal to 300 seconds. All right, so now we know the width of each time interval. Now what we need to do is figure out what the left endpoints are. Here's our table of times again, and the first time interval is from 0 to 5. Our second time interval is from 5 to 10, and so forth until we get to our 12th time interval, which goes from 55 to 60. Now if you look on each time interval, interval 1 is 0 to 5, so the left endpoint is going to be 0. So C sub 1 is 0. On our second time interval, our left endpoint is 5, so C sub 2 is going to be 5. And we keep doing this for each one. All right, so we get that on our 12th interval, our left endpoint is 55. So now we know what our t sub k's are equal to. Now we can calculate our total distance traveled. It's given by this formula. We know what T1, T2, T3 up to T12 is, so we plug those into the formula. Now it says evaluate your velocity at time t equals 0, so that's going to be 1, and multiply it by delta t, which is 300. And then we keep doing that for all of the points along the way, and when we do that, we see that the total distance traveled is about 5,220 meters upstream. All right, so now let's do part B. This is using the right endpoints. We'll still have that our delta t is 300 seconds. But now when we look at this, on each time interval, our t sub k's are going to be the right endpoint values instead of the left. So on our first time interval, the right endpoint will be 5. On our second, it will be 10, and so forth. Here on our 12th time interval, our right endpoint will be 60. So those are the points we're going to plug into our equation here. So we plug in what we know T1, T2 up through T12 are equal to. We now evaluate our velocity at those times, and we know delta t is equal to 300. Plugging all that information in, we get that our total distance traveled is approximately equal to 4,920 meters. All right, so now suppose we have an object and it's not moving in only one direction. Now it can move in both directions along that straight line. When the object's moving forwards, it's going to have a positive velocity. When the object's moving backwards, it's going to have a negative velocity. If I want to talk about the total distance traveled, well, before we said that the total distance traveled was S of B minus S of A. Well, that's no longer the case. That's what we call displacement. That's the difference between where we end up and where we started. To get the total distance traveled, what we need to do is we need to add the distance traveled going in the forward direction, and then add on the distance traveled going in the negative direction. So to do that, what you do is you just put absolute values around each of those distances. And if we do that, then our total distance traveled is approximately equal to this formula. The only change we've made is that we put absolute values around our velocity.